Aziz Talaba, Assalamu alaikum. Welcome to the 5th program in Operating System Program Series. And today we plan to cover the topic of process scheduling. We'll cover considerations in process scheduling. I will look at the round-robin algorithm. We'll also cover priority scheduling algorithm. We'll look at shortest job first algorithm and two-level scheduling algorithm. And apart from that, we will do some exercises in process scheduling. Let's have a quick recap of our previous program. In the last program, we discussed the process model in which we learned that at any given time, there are a number of processes active in the system, but processor serves one process at a time. Although it seems that there are a number of things happening, but actually one process is being worked out by the processor, and we call that concept a pseudo-parallelism concept. We also covered the process states, and we learned that there are 3 process states normally: a running process, which is actually using CPU time, a runnable, or blocked. And in the last session, we also discussed the inter-process communication, in which we learned that processes share some storage in the shape of a shared file, shared variable, or a shared memory. And we learned that in doing so, they come across race conditions, and we have algorithms, process synchronization algorithms, which allow us to avoid or overcome these race conditions. In the last program, we also discussed process synchronization algorithms. We discussed blocking interrupts using lock variables and strict alternation. In the process scheduling, we reiteratively learned that at any given time when the system is initialized, number of processes are in action at any given time. These processes may be system-generated processes, or these processes may be consumer-generated processes. But these processes normally come in 2 varieties. Number 1 are those processes which require CPU time for short bursts. They come, use CPU for a few milliseconds, and then pass away. As yet, we have number of other processes. We can have number of other processes in which they require a long burst or CPU time for processing these processes. Okay. In the operating system, normally the CPU scheduler does not know in advance that how much time a process would take. As such, the scheduler cannot allow any process to indefinitely keep on using the CPU time. In order to avoid the continuous use of the processor by a process, the computers are provided with electronic timers. And that electronic timer create interrupts 50 or 60 times in every second. And we call that 50 or 60 hertz as well. And each computer is fitted with a timer. Although the operating system also allows that you can increase or decrease the number of interrupts per second. Now let's look at this whole game of scheduling with the help of a diagram. Let's look at the diagram. We believe you are familiar with this diagram, that at any given time we have a running process, we have blocked processes, we have ready processes. This diagram is only different in that we have shown more blocked processes and more ready processes, and we have only one running process, because we learned previously that at any given time only one process could be running. And from the running state, the process can go either to a blocked state, if some external variable has to influence that, or a running process go to a ready state. Okay. We briefly alluded to the burst time. Burst time is essentially the time needed by a running process either to complete or go to a block state. If a process is running and that process requires some amount of time, some milliseconds of time, either to complete the process or go to a blocked state. At the same time, we have another time interval called the quantum, and quantum is primarily the time assigned to a process to run before process switch to another process. Okay. Now, here we see there are a number of processes either in the blocked state or in the ready state. How our problem is how to select the next problem which should be running. Out of these n ready processes, which process should be running? And that part of the operating system which makes this scheduling decision is called the scheduler. And the scheme which the scheduler uses to schedule the process is called scheduling algorithm. And scheduling algorithm primarily come in two flavors. Number one, they are either preemptive scheduling, where the processes blocks or switch, as we see from here, from if the process goes from running either to ready state or switches to another process, we call that preemptive scheduling. When the processor can either convert a running process towards the blocked processes or in the ready state in order to give another processor a time, we call that preemptive scheduling. And if we allow the running process the CPU time until it completes, we call that non-preemptive scheduling, where the process runs till complete. Ladies and gentlemen, there are a number of considerations while we are considering a scheduling algorithm or evaluating a scheduling algorithm. And the 5 most important elements or considerations for evaluating or looking at an algorithm are: number 1 is its fairness, number 2 is its efficiency, number 3 is its response time, number 4 is its throughput time, and number 5 is its turnaround time. Now, let's look at all these criteria or all these considerations one by one. The decision consideration, while we talk fairness, because there are a number of processes active at any given time in the system, the scheduling algorithm must ensure that each process gets a fair share of the CPU time. That is one. The next consideration in scheduling or evaluating a scheduling algorithm is its efficiency. Efficiency means that ensures the CPU is busy 100% of the time. Obviously, CPU is a very costly machine, and the algorithm must ensure that CPU is busy 100% of time. In practice, measures between 40% for a lightly loaded system to 90% for heavily loaded system are acceptable. The next important consideration in scheduling algorithm is the response time. As we know, there are a number of users on the system at any given time, maybe from few hundred to few thousands, and the scheduling algorithm must ensure that interactive users get good response time. Again, as we know that system is processing number of batch jobs as well, and the scheduling algorithms must ensure that batch jobs are processed in acceptable time. And the last consideration for a scheduling algorithm is its throughput, and that means the scheduling algorithm should ensure that maximum number of jobs are processed in any given unit of time. Now, that while we have discussed the considerations, the important considerations for looking at the scheduling algorithms, which are fairness, efficiency, response time, turnaround time, and throughput. Now, let us evaluate some scheduling algorithms. The first scheduling algorithm we will look at is the round robin algorithm. The round robin algorithm assumes that all processes in the system have the same priority, and each process is given a fixed amount of time, CPU time, to be used, and we learned that is called quantum. Fixed interval of time which is allotted to each process to run is called quantum, and in round robin algorithm, while all the processes are in the queue and they command the same priority, each process is given a fixed amount of time, and during that amount of time a process is either completes and exits, or after the end of that quantum the process goes into the block state, or the process goes into the runnable or into the ready state from the running state. Now, let us try to understand this round robin algorithm with the help of a diagram. In this diagram we see there are 5 processes: process B, F, D, G, A. At any point of time all these processes are in the system memory, and let us assume B is the current process, and after B takes its share of the quantum, the next process is F, and after F takes after the B's quantum, the situation becomes here. Now, F is the current process, and B after taking its term goes at the back of the end of the queue after B's quantum is over. Now, we assume that the process F completes during its quantum or its share of the CPU time. F completes, and obviously it leaves the queue, and D comes in the next stage and tries to avail the quantum or the scheduled time of CPU allocated to process D, and at the same time another process H enters in the queue. This is why this process is called a round robin. Each process commands a fair each process commands the same priority and same amount of CPU time, and after availing the time the process go at the end of the queue. The main thing, the main issue critical in the round robin is the duration of the quantum. Let us look at with the help of an example. We see here that if our quantum is 20 millisecond and switching time is 5 millisecond, this 5 milliseconds are required to do the housekeeping, means to update the process table. And if we have 5 processes, the 20% of the CPU time will be wasted in switching, will be required for switching. That is not the efficient use of CPU. It means 20% of the time our CPU is busy in switching between the processes. Contrary to that, let us look at if the quantum is 500 milliseconds. If the quantum is 500 milliseconds, then only 1% of the CPU time is required for switching. But at the same time, this can create a response time problem for interactive users. Then what is the solution? The solution is that the quantum should be neither too low nor too high, because if the quantum is too low, quantum affects the CPU efficiency. If the quantum is too high, then CPU time affects the response time. Generally, it is agreed that a quantum of 100 milliseconds is a reasonable duration. Ladies and gentlemen, the next algorithm we'll be looking at is priority scheduling. In the round robin algorithm, we saw that all the processes in the system command the same priority. In practical situations, that is not true. There are a number of business issues which can affect. There are a number of external factors that affect the priority of a process. For example, you own a computer shop which sells the computer time or sells the CPU time, and the consumer or your clients who are willing to pay $5,000 an hour of your CPU time will definitely like to have higher priority than your clients who will be willing to pay, let's say, $1,000 per hour. It means there are certain external business considerations which do not allow that we say all the processes have the same priority. Another consideration is purely on the technical grounds. Certain systems definitely require, or the certain processes definitely require the high priority. How about the air traffic control system? Or how about the control system of the defense mechanism? Definitely these processes would like to have the high priority. And similarly, there is another consideration which is purely the technological consideration of the system itself. Let's understand that with the help of an example. If we have number of processes which require only a few milliseconds of bus time, okay, let's say we have the fixed quantum is 100 millisecond, and we have number of processes which require only 2, 3, 5 or 10 milliseconds. Would you like to keep all these processes who require the shorter bus time hang around in the memory? Definitely not. The system, it is the internal system requirement that these processes who require the short bus time should be disposed of as quickly as possible. Dear students, now let's look at how the priority of the processes are calculated, particularly for the I/O bound processes where the duration, the required bus time is very short. We use the formula 1 over f, where f is the fraction of the last quantum that a process used. Let's assume that we have a process that uses only 2 milliseconds of its 100 milliseconds. What will be the priority? This process will get priority 50, 1 over f. It means 1 over 2 will give us the priority of 50. Let's assume we have another process which used 50 milliseconds from the 100 milliseconds quantum. This process will get a priority of 2. Yet we have another process which used 100 milliseconds of its quantum. All 100 milliseconds of its quantum would get the priority 1. Okay, don't get intermingled with. The larger the number in the priority is better. The process will command a high priority if it is a high number. The process with the priority 50 will command a high priority, and a process with priority 1 will or 0 will command the least priority in the scheduling algorithms. We mentioned that there are certain technical requirements which determine the priority of a process, and it is normally usual routine in the Unix based system, be it a Sun Solaris Unix, be it HP Unix, be it BSD Unix, or any other flavor of Unix. The usual priority scheme is as follows. For example, the real time processes command a higher priority, then system processes command a mid-level priority, and the time sharing processes command the lowest priority. Now let's look at these usual priority routines in the Unix system. These are the typical figures. For example, we discussed the real-time processes have the highest priority, and that priority ranges from 100 to 159. The system processes have the middle priority, and that ranges from 60 to 99. And the system processes priority is established by the kernel at the point when the system initializes. Time sharing processes have the lowest priority, as I mentioned earlier, from 0 to 59. And interactive processes also have the lowest priority, that ranges from 0 to 59. How these priorities are executed in the operating system scheduling arena. Primarily, the various processes are grouped in various priority groups: priority group 1, priority group 2, priority group 3, and so on. And then within that priority group, the round robin algorithm is run. And once the queue in the high priority finishes and there is no more process to be served by the process in the higher priority, the processor shifts to the lower priority processes and then handles that class of processes. And once the second priority process is finished, then the processor move to yet lower priority processes. Now let's look at this, how the priority classes are determined and how these the algorithm, priority scheduling algorithm, handles various priority classes. Let's look at with the help of a diagram. As we see in this diagram, we have priority class 4, priority class 3, priority class 2, and priority class 1. The priority class 4 is having the highest priority, and we can have and consider this as synonym to the real-time processes. Real-time processes fall, let's say, in a priority class 4, and we have number of processes 1, 2, 3. Within these processes, the round robin algorithm is implemented. Once the processor is finished with this priority class 4, the processor moves to priority class 3 and starts serving the process 1, 2. Let's say we have only 2 processes here. Once the processor has done with this priority class 3, the processor comes to priority class 2 and starts serving it, and so on, it comes to priority class 1. The only problem with this priority classification is that the priority class, lower priority classes may starve to death, because once the processor is serving from 4 to 3 to 2, let's say the processor is at priority class 2 and another process in priority class 4 comes, the processes will jump back to the higher priority class and may never come to priority class 1. That is the main problem in the priority classification. The next scheduling algorithm we'll be looking at is the shortest job first algorithm. If we know that how much time a process is going to take in advance, and we know that how many number of processes we are going to run, then we can use shortest job first algorithm. And if we know the time in advance, that how many minutes or how many hours or how many seconds our batch processes would take, then if we use shortest job first algorithm, that will give us the lowest average time to complete each process. That is why the shortest job first algorithm is best suited for batch jobs. How the shortest job first algorithm works, let's look at a diagram. You see, we have 4 processes. process runtime for process A is 8 minutes. For process B, it is 4 minutes. For process C, it is 4 minutes. For process D, it is 4 minutes. Okay. If we run this as is, the first process having the highest process time, if we calculate the turnaround time for process A, it will be 8 minutes. Process B will be completed after 12 minutes. Process C will be completed after 16 minutes, and process D will be completed after 20 minutes. Now we calculate the average turnaround time. We see 8 plus 12 plus 16 plus 20, we have 56 divided by 4. Average turnaround time for these processes is 14 minutes. Now let's use the shortest job first algorithm. And in the shortest job first algorithm, let's say we do bring the process B first, process C, then we bring the process D, then we bring process A. The turnaround time will be process B will be completed after 4 minutes, C will be completed after 8 minutes, D will be completed after 12 minutes, and A will be completed after 20 minutes. Now let's calculate the average turnaround time. It will be 4 plus 8 plus 12 plus 20. It will be 44 by 4 equal 11 minutes. We see here, if number one, we know the process time in advance, we know how many processes do we have, then we use shortest job first algorithm, because that gives us better average turnaround time. Dear students, this wraps up our today's discussion. In today's session, we looked at the considerations in process scheduling, and then we looked at a round robin algorithm. We looked at priority scheduling algorithm, shortest job first algorithm. This wraps up our today's session. Thank you, and Allah Hafiz.